In this video, I'm going to introduce you to another approach to stacks, which is a linked-based approach. There's two main reasons that we're going to explore a linked-based approach to a stack. The first reason is that we want to be able to control the underlying data storage of the stack data. And what I mean by that is that I don't want to use a built-in data type like a list or an array. I want to be able to create my own way of storing the data so that I can ensure that the data storage is as efficient as possible. The second reason that I want to show you this now is because we're going to use it a lot in data structures. Data structures are often going to rely on this kind of structure or pattern, so it's best to learn it with a simple data structure rather than when we get to trees or something like that and we start talking about this idea and it becomes like a lot to learn all at once. The idea of a linked-based data structure is taking a look at the idea of storing data that is what we would call linear. One item follows the other, so it's like a sequence of data. In this sort of situation, what we can do, rather than storing everything inside of a list of data, is that we can actually abstract this down into a simple idea that we have a value and then a pointer to the next value in the sequence. So we could create a data structure that basically just stores a value and then a pointer to the next thing in the sequence, and then we can create this chain of values that are related to each other. And that data structure we would often refer to as a node, or that's what I'm commonly going to refer to it in this course as. So the idea of our node data structure is that it really is quite simple. Basically, all it does is it has, a class node, and then it's going to have this initialization function, and it's going to have a value, and it's going to have a next. And we usually pass these in as arguments. And so basically what will end up happening is that we could create a sequence of values just by giving this a value and a next. Let me show you a little bit about what I mean by this. So suppose that we had a value a, which was a node, and it had a value of 1, and maybe there's no next currently, so that will be none, just to start off with. Then say that I create a second node, b. It has a value of 2, and it's going to point to the node a. What happens here is basically if I wanted to look at this sequence, the first item in the sequence is b, right? So if I print out b.value, that's the first thing in my sequence of values here. If I want the next thing in the sequence, what I do is I print out b.next.value. That gives us the thing that comes after b, which is a. And what you'll see from this sort of result is that when I actually run this, right, we get the value 2, followed by the value 1. Do you see how we create a sequence of values using these nodes, right? So understanding this idea, let's see how we can implement a stack using this sort of concept. The main idea here is going to be that the stack is going to keep track of the top as a node. It's going to start as none because there's currently nothing on the stack. I'm going to keep track of the size as well because now I don't have like a length property on an array. So those are the two things that I'm going to keep track of. When we go and we push a value onto the stack, what we do is we create a new node. And that node needs a value as well as something to point to, the next thing in the sequence. So when we first add something onto the stack itself, what happens is that value becomes the new top of the stack. And you have to think, what would that thing point to, right? Well, it would point to the old top of the stack, right? So we basically place this thing at the top, it then points to the next thing in the sequence, which is what used to be at the top of the stack. And if we keep doing this, it preserves this chain or this sequence of values so that we have this stack available to us. So basically the value of this would be the value that we're trying to push onto the stack, and its next would be self.top. Then what I do is I set self.top equal to the new node, and then I just increment my size by 1. So let me show you just a little bit about what that's going to do, right? So if I were to set up a new stack, what I could do is I could push on some values onto it, right? And what ends up happening is, so after this first push, we get the value 1, which is the top of the stack, and it points to nothing, right? When I push 2 onto the stack, what happens is the first thing I do is I create a new node 2, which points to the current top, which is 1. 2 becomes the new top of the stack, and we increment the size. So this is our new sequence of values. When I go to push 3, again, 3 points to the current top, and the current top is already pointing to 1, right? So you see that this whole sequence was already preserved. By adding 3, we just point something new to the top and make it the new top. Do you see that we just sort of like place it at the front, and the sequence continues on exactly the way that it started? Basically, each node just keeps track of the thing next to it, and that in turn creates a sequence of values for us to be able to work with. The beauty of this sort of process is that creating this new node is just storing some data, right? It's O1. This update here is O1. This here is O1. This whole method is constant time. There's no amortization. There's no additional operations required. It's a very strictly O1 implementation because we've controlled the underlying data structure for how this is working. And like I said, you're going to see this structure a lot of times, so this will become very familiar and easy as we continue on. So don't worry too much about like all the fine details. It will start to become more clear as we continue on through this. For now, let's finish off our implementation, right? So we have our push operation here. The next thing that we would need is a pop operation. A pop operation follows the same sort of pattern as before. What we do is we start by checking the size of the stack. If the stack is greater than 0 in size, well, then we're going to actually pop the value off. How do we pop a value off the stack? Well, first I need to know what's at the top of the stack so that I can return it. I'll call that my ret value or return value. This will be self.top.value, so that's the value at the top of the stack. From here, we just update the top to be equal to self.top.next, the thing that follows it in the sequence. Finally, I decrement my size, and I'm going to return back the value that was at the top of the stack. So it's a bit more steps, generally, than what we had before, but that's okay, right? Still the same sort of process of removing a value from the top. Let me just put in the else statement here, and then we'll just talk through this method as well. So on the else, I'm going to raise my exception of a stack underflow, right? So there we go. So let's talk about the pop here, right? So when I go and I do a pop off of this stack, right? So we pushed all these values on. What happens is the top gets updated to be the current top's next. So the top gets valued to be 2, which points to 1, which points to none, right? The value 3 has been effectively removed. It's no longer in this sequence at all, and it gets returned back as a result. Do you see how that generally is going to work in this process? 3 gets removed out of the chain. The top gets moved forward to now point to 2 instead. So we've removed it from the sequence of values, therefore removing it from the actual stack itself. That's generally the way that this process is working for us. One final method that we need is peek, right? Peek is the easiest, really. If the size, right, is greater than 0, all I need to do is just return self.top.value, the value that's at the top of the stack, right? And then on the otherwise, I'll just raise my little exception for a stack underflow, right? Nice and easy. And then generally, I would say just for completeness, we could do the same sort of idea as before with the size method. In this case, it's really not that necessary since we could just, access self.size directly. I just want to raise this in case you're working with a language like Java, which has like the private methods, that sort of idea where we can't access that property, right? So that would be the main reason why we may want to do something like this. So that's the general idea of our stack here. So let's just walk through a few different operations here. So I'm just going to print out these pop methods, right? And we'll just do similar to before. We're going to print out the pop methods, and we'll print out the peek as well. And we'll just take a look at what those results end up looking like. They're going to be consistent with our previous example, right? So if I do my Python 3, we'll do chapter 3 node.py. Do you see that, we peek the value 3, and then we have 3, 2, 1 as our pops, right? So you see that it gives us the exact same results. Just in this case here, we get a bit more of an efficiency because our push is now O1. When we take a look at our pop, again, we're just updating memory, so it's O1. And this here is, of course, O1 since we're just accessing data off of the stack, right? So this gives you another approach to actually doing this, this process of implementing a stack, right? You'll probably more frequently see the array-based stack when you take a look at, practice problems online. It's the easier of the two implementations to use more directly. This one requires a lot more code to actually get up and running. I just wanted to give this to you as an example of a way that we can improve the time complexity and also to get you to start thinking about this idea of linked structures. If you haven't worked in lower level languages, say like C or something like that, the idea of pointers may be a little bit weird to you at first, right? But I want you to start to think about it, start to get familiarized with it. We'll continue to see it throughout the course, so it's not going to be too much of a problem. By the end of it, you'll be an expert with it. I just want you to start thinking about it now, start to get familiarized with it before we start to get onto more complex ideas. So that finishes off our implementation of stacks, and we'll move on to actual examples of using a stack for practical problems. Thanks so much for watching. I'll see you in the next video.